Okay. All right, students, let's get going. This is the last lecture of the year, and I want to say it's been a lot of fun getting to know a lot of you and observing a lot of you, even though I don't know everybody's names. I've tried to learn names, but it's been a lot of fun for me. We've learned a lot. We're going to talk about molecules and stuff, and we're going to end up talking about the polar structure of the water molecule. And then we're going to have an in-class clicking review for the last 20, 30 minutes. We've got handouts. You'll click them in self-paced mode as if you were on a test. So have your clickers ready. Plus we have regular clicking as well. Now, before we get to that, I'd like to mention that the schedule page for SSG is almost ready. Now, we only have one person that hasn't given me his SSG, and that's Sean Tiernan. Are you here? Okay. Everybody else is. So if you haven't looked at that, I last updated at 7:46 this morning, and all but one person is on the schedule. So you can look around that. And sign-ups will begin tonight at 9 p.m. All right? And so you can storm in there and get it. Now, our main topic today is molecules. Last time we talked about this concept of molybus, which is from the Latin word, large, shapeless, huge bulk, for which this phrase, appugnat molybus urbum, was famously used. From it, we get the word molecule, which means, when you attach the cule, means a small part of the bulk. So the molecule concept is the idea that there's a small part of every big piece of matter or sample of matter that you look at. And here's a picture of the methane molecule, CH4, a carbon in the middle, and then 4 hydrogens attached to it symmetrically, forming a pyramid shape. I don't know, can you see that that's a pyramid? It's supposed to be tetrahedron, they call it. Now the guy that kind of locked all this in and really verified the concept of molecules was Avogadro. Lorenzo Romano Amadeo Carlo. Okay, Lorenzo Romano Amadeo Carlo Avogadro. Kind of an interesting guy. Came from a family of mostly lawyers, jurists in Italy, roughly, 200 and something years ago. And in 1811, he made a famous hypothesis concerning molecules. So let's review some of the ideas of the molecule versus the moles, the shapeless bulk. Molecules we now measure in atomic mass units. And as I mentioned last time, we base that on the idea that the very, very common carbon molecule, the carbon-12 atom, is exactly 12 atomic mass units. And that notation there, capital C, with a 12 upstairs, a superscript above, in front of the letter C, the capital C, that's another way of writing the word carbon-12. Okay, so 12 atomic mass units, and that's a little different way of defining mass, but it's good for atoms and molecules. So, for instance, common hydrogen atom is 1 atomic mass unit, and although there are isotopes of hydrogen that exist in nature, they're fairly rare. We talked about isotopes last time. Deuterium and tritium are the 2 isotopes of hydrogen. It's basically a proton and a neutron in the nucleus for deuterium. Deuter, D-E-U-T-E-R, is Greek for 2. Tritium, that means 3. 3 items in the nucleus of the tritium isotope. And that's 2 neutrons and 1 proton. Helium atom. There's 2 different flavors of helium. All of them have 2 protons in the nucleus, but the helium-3 has 1 neutron. Helium-4, which is pretty common, is actually has 2 neutrons in the nucleus. So total of 4 atomic mass units. Another thing that you can do is give an atomic mass rating to a molecule. All right, so for instance, carbon dioxide would be 44 AMU. Now let's take a look at that in specific detail. Carbon dioxide, that means 1 carbon and 2 oxygens. Let's look at the periodic table. Here it is. And what we're going to do now is do a close-up view of carbon and oxygen. They're over here. Let me get my cursor. All right, here's carbon and oxygen in the northeast corner. Let's focus in on them. And I'll burn in a little rectangle around each one. Okay, carbon, in this periodic table, the mass number's in the upper right of the cell. And they got other stuff down the bottom. But yeah, carbon is 12.0. Oxygen is 16.0. So 2 oxygens is 32. And 1 carbon is another 12, so that's 44 total. All right, so make a note of that. If you look at the periodic table, you can figure out the mass in atomic mass units of a molecule. And sometimes it's hard to know the exact formula of a molecule. But yeah, CO2 is fairly easy to figure out. And we've known that for over 100 years. Now, let's get to the shapeless bulk, the moles, molybus. Now, this is a word representing a large sample of an element. So, in other words, a macroscopic scale piece of carbon, or a macroscopic scale vessel filled with CO2, or any other substance that you care to name. And so the macroscopic mass scale that we normally use is the metric kilogram or gram. All right, so we're going to use grams. And as you know, a gram, the mass of a gram, is basically based on the mass of a cubic centimeter of liquid water. You know what? In Paris, certain temperature, and so on and so forth. So it's liquid. And here's how we apply this mole and molecule idea. Avogadro said, take any mole, any molybus, any shapeless bulk, so a liter of CO2, and then take a liter of hydrogen gas, for instance. And if they're both at the same temperature and the same pressure, then those 2 liter containers have the same number of molecules. All right? And so that was his conjecture, and he reasoned that that was the case because he felt that if molecules exist, if all the molecules of CO2 are the same, and if they basically obey F equals ma, then equal pressure and volume should correspond to equal number. And it's been verified. He was correct about that. So that leads to this logical question. All right. Instead of thinking in liters, you can ask yourself, well, okay, how many molecules are there in 44 grams of CO2, right? You could ask, okay, how many are there in a liter? But if you ask in terms of the atomic mass, so if you say, all right, 1 unit of CO2 is 44 atomic mass units. So if instead of using atomic mass units, I use grams, how many are there in 44 grams? It'll be some multiple of, some number. It should be a whole number. So if the exact mass is 44, then 44 grams ought to be an exact whole number of molecules. And in the metric system, that number is called Avogadro's number, N subscript A. It's a 6.022 times 10 to the 23. It's a huge number, and it would be even larger if we were using English units. So, you could say, well, okay, how many atoms, or excuse me, how many molecules of CO2 are there in 44 grams? Or you could say, how many are there in 44 pounds of CO2? All right, we could use that. The British Thermal Unit, BTU, that's that's oriented to water, a pound of water, and Fahrenheit degrees. All right. So if we were using the English system for Avogadro's number, it'd be quite a bit bigger number than this. 44 pounds or 44 ounces of carbon dioxide. But we're using the metric system, and it's a weird number, but it basically is a way for us to relate the shapeless bulk, the molybus, to the molecule, the tiny constituent. Now I have a clicker question for you. Let's try out a computation of a molar mass for another compound. All right, and this is going to be a fairly simple compound. I'm going to give you a little slice of the periodic table. All right, here it is. What's the molar mass of nitric oxide? NO. 1 nitrogen, 1 oxygen. And you've got a slice of the periodic table there. You can figure it out from this. Okay, so take a minute to calculate that. Darian, you know what Caroline and I found is on this, if you touch that.
That's convenient.
Yeah, you can grade it immediately. You can also do it on numeric questions as they come up. And you can look, if you know the answer, you can click on them. For multiple choice, you only have to do it once. Okay, 15 seconds to vote. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay, there's 74 students clicking, so you should have a... Okay, good. All right, answer. Most of you got it correct, 82%. And for those of you that didn't get it correct, here's the rundown. You look at nitrogen and you say, all right, what's the mass in atomic mass units? 14.007. And then you got one of those. And then you got an oxygen. So you look at the mass number for oxygen, 15.99. And then you add them together, 30.06. And so there's your answer. Now, we're going to keep working on different concepts here. We'll continue talking about carbon and the orbitals and the different orbits. We're going to talk about n equals 1 and n equals 2. Okay, because carbon has, those are the lowest energy levels for a full carbon atom. So energy level n equals 1. The orbital angular momentum state is actually 0. It's orbiting, but we consider its orbital angular momentum to be 0. That being the case, the intrinsic spin angular momentum of the electrons is either up or down. There's two flavors of electrons, and that's all that's allowed in n equals 1. So the total populations for the n equals 1 level, and this applies to any atom. For n equals 1, 2 atoms only. A spin up electron and a spin down electron. All right, and that's it. So here they are. I've sketched them in. And notice what I've done. I've sketched in 2 little blue dots. And up here, I have one of them with a little arrow pointing upward. And down here, just kind of random positions. Another blue dot with the arrow pointing downward. All right, and that's to represent the spin state of the electron and no orbital momentum, no orbital angular momentum. All right, so that's energy level n equals 1. Now carbon has another four electrons, total of 6 for a neutral carbon. All right, so energy level n equals 2. Now this one can have two different angular momentum states. It can have L equals 0, okay, higher energy level, but it can still have the L equals 0 angular momentum state. And it can have L equals 1 angular momentum state, orbital angular momentum state. All right, now, as you can read in the textbook, the magnetic field, if you apply it, will split the L equals 1 into 3 suborbitals. All right, and the intrinsic spin is up and down, so that's a total of another 6 and a total of 8 in energy level n equals 2. So there's 3 suborbitals, 2 each, and then L equals 0, 2 each. And so you have a total of 8 orbital states available, but for carbon, you only have 4 electrons up there. And this is an important factor. Yeah, carbon would like to have that entire n equals 2 level filled with another 8 electrons, but it's only got 4 up there. All right? Because carbon is carbon 12, 6 protons, 6 electrons. So here are your 8 possible states, but we're going to erase a couple of them. All right? So go ahead and erase 2 of those or cross them out or something. All right? So there's 2 sets of up and down for carbon in the n equals 2. And another 2 sets of up and down it would like to have. And if it did, then n equals 2 would be completely filled. Those outer electrons, these ones over here in the n equals 2, they're at a higher altitude. They're easier to ionize. They're already halfway out. Kimmy, they're partway out of the carbon atom. They're at a high potential energy here. A little bit more energy, and bang, they're completely out. All right? So those ones are called the valence electrons. And those outer electrons, there's 4 of them. Those are the ones, valence means to move, to motate. All right? And those are the ones that will move and create bonds with other atoms, like oxygen and carbon dioxide. All right? So, valence electrons. Let me pause for questions. Is it getting cooler? Does it feel a little cooler? Good. I think so too. I'm glad we opened up these windows. All right, let's keep going. Let's talk about bonding. So, here's the thing that you want to remember. Every atom will try to bond with something and complete so that it fills its outer energy level. So for carbon would like to get 4 more electrons. Then its outer energy level would be filled, and that would make it like one of the noble gases in the far right column of the periodic table. Now we're going to take a look at that in a minute. All right? So this whole idea is that the outer shell should be full. And if you add electrons to carbon, 4, you'll get a full shell. If you subtract 4, if you ionize the carbon and boost the 4 that it already has, if you boost them out of there, that will make carbon happy, because then the n equals 1 level is the full shell. So here's a picture of the periodic table. Make a note. This is the far right column. We call them the noble gases. Everything in this rightmost column has a filled outer energy level. Okay, helium is full. It's got n equals 1. That's all it has for its ground state. And it's got 2 electrons in its neutral configuration. And so that's considered full. And because of that, helium does not make chemical compounds very readily at all. You can kind of force it to make a compound, but it won't be very long-lived. Same thing with neon. Neon here is the next noble gas down in this column. Neon has an atomic number of 10. That means its n equals 1 level is filled with 2, and its n equals 2 level is filled with 8 more, total of 10 electrons. So neon is happy as the proverbial clam. Argon is next, and argon is 18, right? Another 8. It's happy as the proverbial clam, and so on down. Right now, when you get to the heavier ones, it's a little bit trickier. You know, the law of 8 and stuff gets a little more complicated to apply. But for the first 2 or 3 rows, it's not that bad. And there's a huge amount of different compounds important to human life made from hydrogen all the way to argon, or hydrogen all the way to chlorine. Right? So let's take a look at bonding. All right? And here's a slice. Let's take a look at the upper left corner of the periodic table and think about bonding here. Now, the idea is that the outermost orbitals are the ones that are involved in the chemical reactions, those valence electrons. And that's because they're not as tightly bound. They're at higher altitudes. They're easier to ionize. If it was a spacecraft at a high altitude orbit, you could say, well, I don't really need much rocket fuel to get to the moon, you know, to leave Earth's gravity and get to the moon. All right. Same thing with atoms. You know, if it's a higher energy level, n equals 2 or whatever it happens to be, that means to ionize it, or to steal that electron, whatever way you steal it, it's easier. So those are the ones that get stolen. So when you're, you know, the proverbial 5-finger discount, when you're talking atoms, it's the outer electrons that get the 5-finger discount. Okay, so the outer orbital electrons are the ones that are mostly representative of the or mostly responsible, I should say, of the chemical properties, for the chemical properties of the element. And a case in point is the first column. All right? Hydrogen, lithium, and sodium. Now, they're over there on the far left. They have a filled energy level +1. Okay? So lithium is element number 3. It's got n equals 1 filled in its ground state. And then it has one more, a neutral lithium. A neutral lithium atom has 3 electrons. So it's just got 1 out there in the n equals 2 level. And it's out there kind of poking around. And it's not bound very strongly. And that's the one that another atom can rifle. Same with sodium. Sodium's got 10 +1. And that 11th electron in a neutral sodium is the one that can get rifled. And who rifles it? Chlorine. Chlorine is all the way on the other side of the periodic table and wants to get 1 more electron. And if it does, it'll form an ion and we get sodium chloride, salt. A positive sodium atom bonded to a chlorine with a stolen electron and therefore a negative chlorine ion. And they bind together ionically. That's an ionic bond. In addition, the energy levels are quantized. Now, I want to take a look at the bonding structure or the bonding procedure for carbon dioxide. All right, so here we go. Let's take a look at the periodic table again. All right, eyeballs up. Take a look at what we got. Now, over here on the far right, there's your noble gas column. Now, oxygen is over there 2 slots to the left of that. Carbon is 4 slots to the left. And that means that carbon would like to get 4, and if it had 4, it would have an outer energy shell like neon. Oxygen Well, here, let's take a look at it. Carbon, here's a close-up. All right, go ahead and make a sketch of this slice of the periodic table. It's the important one for us. Okay, carbon, it's 4 slots over from neon, and so it's got 4 valence electrons. If it can steal another 4 or share another 4, then its outer energy level will look like neon. All right, so I made this curvy arrow to bump 4 units over, 1, 2, 3, 4 to neon. So carbon, yeah, carbon can do that. If carbon can grab another 4, then it's going to be happy as the proverbial clam. Now you may be saying to yourself, Dr. B, I have never seen a clam that was happy or sad of any kind. Clams do not normally express emotions. But it's a proverbial saying, so let's just, and here's another, oxygen. Ching, 2 bumps, and oxygen is over at the neon state. So if oxygen can get 2, it'll be happy as the proverbial clam. Okay? A crustacean from under the sea. A clam. All right? Now, here's the cool thing about carbon. Yeah, carbon would like to have 4 more, but carbon has this property. You could also go 4 fewer. Grab 4 or lose 4 is the story for carbon. And this is actually why it combines with so many other elements. You know, we're considered, here on our planet, we're considered a carbon-based life form. And this is one of the reasons. There's a lot of carbon on our planet, and carbon is an atom that is easy to make compounds with. Because so here we go. Let's lose 4. Now, I've animated this, and I've got a lot of flames burning here. So take a look at these burning flames. All right? I don't see everybody looking at. All right. You ready? All the way in the back. You ready to look? Yeah. Yo. Okay, no, the girl in back of you. Yeah. Okay, you ready to look? We're burning off some. Okay, so we're going to burn off some electrons. Carbon's got those 4 valence. Let's burn them off. All right, here we go. Boron, beryllium, lithium. That's 3 gone. Now burn off 1 more. Bing! You're all the way over to helium. So now, if carbon loses 4, its outer energy level is the N equals 1, and it's happy as a clam. Okay? A clam really deep down under the sea. Now, that being the case, let's put it all together. Here we go. Carbon 12, N equals 1, N equals 2, 2 electrons on the N equals 1 in the ground state. And carbon 12, N equals 2, 4 electrons up there. All right? And a neutral ground state electron. All right? Oxygen. Let's look at what we got here. Okay? N equals 1, N equals 2 oxygen. 2 electrons. 1 up, 1 down in the N equals 1 energy level. And now oxygen has a few more. It's a little bit to the right of carbon in the periodic table. So we've got 6 electrons up in the N equals 2. All right? Now, here's what we're going to do. We're going to take those 4 carbon electrons, the 4 valence electrons from carbon, and we're going to burn them off. And who's going to get them? The oxygen. Because the oxygen would like to have 2. So if you take 2 oxygens and you say bye-bye right here to the 4 that you've got from carbon, and you say, all right, I'm going to share those over to my oxygens. Here we go. Right? Bye-bye. And then your occupied, fully occupied energy level is n equals 1. And that's like helium. And then, all right, here's those 4 valence electrons, jing, they go over to one oxygen, and then cha-ching, they go over to the other 2 go to the other oxygen. And now oxygen is happy as a clam under the sea. The SpongeBob. Is SpongeBob a clam?
No, he's a sponge.
Oh, yeah, that's right. He's a sponge. Does he have friends that are clams?
He has a baby. Yeah, he has a baby. There's also giant clams.
SpongeBob has a baby?
Yeah, him and his sister. It's an episode.
Really? How come you guys know so much about SpongeBob?
Yeah.
Is this related to Justin Bieber as well, or
No.
you met Justin Bieber? See, I knew that was true. I knew that he wasn't nice. Anyway, so happy as SpongeBob under the sea. All right, so here's what we got. So now, in this compound that we formed, the outer energy level and all your electrons in the ground state, yep, n equals 1. So that means that those electrons are like a helium set, because that's all that helium normally has. Now this is an ion. If you lose it, it would be an ion. If you share it, it's still a carbon atom. And now over here, the 2 oxygens have got 8 and 8 in the outer, and that's like the neon outer shell. So it's got a good helium inner shell, and then the n equals 2 shell is configured like neon, and that makes the oxygen atom happier than SpongeBob under the sea. And that's the compound that we call carbon dioxide. All right? Now, I'm going to bring in the waves concept, de Broglie waves concept, and show you exactly how the waves concept, the electron wave function, brings about bonding. Because all these bonds are something we call covalent. In other words, you're sharing the valence electrons. Here we go. If you have 2 atoms that are fairly far apart, this is actually the shape as you go away from the center of the atom. This is the shape of the wave function. It's kind of a peak. It looks like 2 mountains. So this is 2 atoms. The wave function is symmetric left and right around the atom, and then it's actually this is actually the radial profile. So it's a quantum wave function, and this is the amplitude. So right in here, if the 2 atoms, the 2 mountains, are far enough apart, they don't really overlap. Okay, so make it so that there's a broad, deep valley between them. All right, the amplitude down there, it's not constructive or destructive. It's just there's not much waves going there. All right, so you got flat water if they're far there between them, if they're far enough apart. Now, as you bring the atoms closer, you're going to bring the mountain sides here of these mountain-shaped wave functions a little bit closer. You can get them to overlap. All right, now here's what the overlap looks like. All right, here's what you can see in dotted lines here, the original wave functions, and then the solid line shows the sum of the wave functions. So this would be like with the audio signals, signal 1 and signal 2, and then the combo signal. In this diagram here, the solid red line there is the combo signal. All right, and in quantum mechanics, what we actually study is the square of the amplitude. Right? And that's this next diagram over here. And it's got 2 peaks. It's a little bit deeper of a dip. But if you look at it carefully, This is like two mountains that have come closer together. And now you've got a plateau between them, a tableland between them that it's not flat water. That's high water there. You've got constructive interference. Okay, so what happens in there? If you do all your calculus and use imaginary numbers, where I squared is equal to -1, you can do all the math and stuff and show that that's constructive interference. And because of that, because you get constructive interference, the atoms like that. That is the bond. That is covalent bonding. Covalent bonding exists because because electrons really are what de Broglie said they were. De Broglie said, I think that electrons behave as waves. And somebody could then, if somebody could have said, all right, de Broglie, somebody already checked electron diffraction, I'm going to check covalent bonding. It should work. So they could have predicted this. I don't know if they did, but this is a direct result of de Broglie's hypothesis. All right. Before that, the ionic bonds were easy to understand. Electrons being stolen by one atom from another, and then individual ions bonding without any wave interaction. This is different. This is a quantum effect. Now, let's take a look at the covalent bonding and constructive interference situation for H2O. Now, I'm going to take a look at my picture. Make a sketch of this if you want. You're going to need to do another sketch because I'm going to rearrange this. All right, so this is the status where the atoms are far apart. So I have two hydrogens over here. Here's a hydrogen, a +1, and an electron. And here's another one down here in the lower left, +1, proton, and an electron. Over here on the right is a big nucleus, +8. That's my oxygen nucleus. Now, I haven't put any neutrons in there. I just put +8. Right? That represents the nucleus. And kind of around there, I've kind of sprinkled in, I just kind of threw them in there at random direction, positions. I've got 8 electrons. Now, the only thing I did when I put my electrons in here, I put 2 of them down close. So these 2 down here are the n equals 1 electrons for the oxygen atom. Now, they're not going to do any of the chemical bonding normally, right? The chemical bonding is going to be with these outer babies, all right? And then chemical bonding, covalent bonding, here's the other electron wave function right here. Hydrogen, so we're going to move one hydrogen mountain over to the oxygen mountain. Let's see if we can get some overlap. And then we're going to do the same thing with this hydrogen. We're going to go around to the south side of the mountain, of the oxygen mountain, and move it in. And see if we can get some constructive interference. So the first thing that we're going to do is this. Right now, take a look at this. See this electron? Lower right. Look at it. See it? I'm going to move that out of the way. Over there. Now that's on the back side of my oxygen. And why is that? Because I'm going to start moving in these electrons. And now make a sketch of this and this. All right? There are my hydrogens, and now I've moved them in so two of my blue dots down here at the bottom are overlapping. There's your covalent bond. Kind of a pictographic representation of your covalent bond. And here's another little overlap action up here in the upper left. All right? Now, because those hydrogen atoms have zoomed in there closer to the mountain, the other electrons are going to want to redistribute themselves and kind of motate over. So that's why I brought this one over here. And that is why this is the negative end of the oxygen molecule. And then the positive end is the hydrogen end of the oxygen molecule. All right? And I've got it just about right for shape. Here's a real precise shape for water. The polar structure of the water molecule. My wonderful students, the electrical structure of the water molecule is why it is the water of life. It dissolves all the nutrients that we need. You couldn't make life if you didn't have water, we don't think. Maybe there's a way to do it. But this structure, this polar structure, allows all kinds of molecules to attach positive to negative to water. Question?
For the old, the other ones, why did it have to be that electron? Why did it pair?
This one? This one right here?
Yeah, why did it?
Well, I knew that I was going to bring this one over here and share with this one. And I knew that this lower hydrogen, I was going to try to get it to share with this one. And this electron is going to bolt out of there because it's going to try to avoid this one, this hydrogen, the lower hydrogen. It's going to try to avoid this. So if I bring those mountains in, this one's going to try to skedaddle. All right? And so I just said, all right, let's just, kind of symbolically park it over there to that side. And then as I bring in, these two babies. So those electrons that are now sharing, the valence electrons from hydrogen, have chased this electron that I moved to the other side of all the way to the other side of the molecule. Right? And you could do all kinds of computations of, the rough distribution of charges and stuff. But roughly speaking, that end of the oxygen molecule, or that end of the oxygen atom, and that end of the water molecule is going to be slightly negative on average. Okay, it's all waves. I mean, it doesn't work. Nothing works if you think in terms of particles. But these particles help us to think about what's happening. So I've got overlapping circles to represent constructive interference covalent bonds. Okay, another question. Water. Students, for those of you that have to take another science class, if you take intro chemistry, you'll be ready for it now. Whatever the chemistry class is. And if you take astronomy, you'll be able to understand a lot of astronomy too, because this molecule is what half the astronomy PhDs on the planet are looking for. We're looking for it in planets. We're looking for it in the planets of our solar system and the planets of other solar systems, other star systems. And we find the signs of water, the spectrum of water, everywhere in the universe. By the way, I am Darian. My fall teaching semester, my fall teaching schedule, I have 2 big lecture sections of Astronomy 2002. I don't have any big lecture sections of this. Yeah. So for those of you that want to avoid having me for your next class, I'm going to be teaching Astronomy 2002, sections 2 and 3. So, but if you want to have me for astronomy, I'd love to have you. And that's next fall. And after that, who knows? All right. Now, your exam will cover everything up to my discussion of water. You'll have some homework tonight about this lecture today, water and polar structure and everything. You'll also have a big, huge review homework. All right. And what we're going to do right now is a clicking review. All right. And Darian is going to hand out some papers. Can you turn the lights all the way up? And we're going to do clicking